Okay, this is problem number 7, section 3, chapter 8. It's the trigonometric integral. So we have sine to the fifth of 2x. I think it is, not 5x. Times cosine of 2x dx. Okay, what we're going to do, we're going to use trigonometric integration, but we are going to have to use kind of two substitutions. The first substitution, I'm going to use w instead of u because I'm going to use it later. W is 2x. It's the argument in the trig function. So if we take the derivative, so we're like using kind of like u substitution here. So we're calling it w to not confuse ours. So the derivative of 2x is just 2, and we add the dx. So we have dx in the original integral, so let's solve for dx. It's going to be dw divided by 2. So when I make those substitutions into the original integral, I get sine to the fifth of w times the cosine of w times dw divided by 2. The second substitution I'm going to use is to get this into a polynomial type situation, because that's what happens when you have trig integration. And we see we have cosine of w, we have sine of w. So this is a pretty simple one in that we would take cosine of w, put it with dw, and then let u, in this case u is going to be the sine of w. Therefore du is equal to the cosine of w times dw. So now we can rewrite it again. The second substitution, I'm going to factor out the 2 in the denominator. So this 2 comes out. The sine becomes u, so I end up with u to the fifth power. And then I've got cosine of w dw, which is du. Okay, now we have it in a form that is something that we know how to deal with. So the power rule problem. So the integral of u to the fifth is u to the sixth divided by 6 plus some arbitrary constant c. So since I did two substitutions, first a w substitution, then a u substitution, then I have to go backwards. So I'm going to do this one first, and then I'll go back there. So let's factor out the 6. So we get 1/2 times 1/6 is 1/12. U is the sine of w to the 6th power plus c. And then we do the second substitution, where w is equal to 2x. So the original expression was sine to the fifth 2x. The result is sine to the sixth 2x. We end up with this factor of 6 because of this integration. We've ended up with a factor of 2 here because of the fact that we have the sine of 2x instead of just the sine of x. If we had originally the integral of the sine to the fifth of x cosine to the fifth of x dx, the answer ends up being 1/6 instead of 1/12, the sine to the 6th power of x plus c. So you miss out this factor of 2 that comes from the fact that the original integral was 2x. If I had cosine of 3x to the fifth, then I end up with another factor of, instead of 1/12, I'd probably end up with 1/18. And that's how you handle when you've got a trig integration that is not just simply x. It has some other variable. You have to do the second substitution and then do the double substitution on the way back down.
Adjacent side length over the opposite side length. You remember that the tangent is opposite of adjacent. So
I had my mute on, so I didn't hear my normal thing that tells me I'm doing everything correctly, but I'm pretty sure I am. So we'll see what happens. Okay, so problem number, first problem out of section 3, chapter 8, is the integral of the cosine cubed.
So the answer will be negative.
Actually, it's the sine, sorry.
The cotangent of theta, which is
sine
the square root
cubed of x
of
dx.
25 minus x squared divided by x.
So we can't
and that all
choose the cosine of x to be cosine of x dx to be du. So we're going to use the sine grouping that to the side. So if we do that, we'll go from being sine cubed to being sine squared times the sine times dx. So we still sine cubed of dx, but we combine these two. So this is going to be du, so u is going to have to involve something to do with the cosine, but we're in the sine squared, but because it was an odd exponent, we can use the Pythagorean identity, and that says that the sine squared of x is equal to 1 minus the cosine squared of x.
I know that the sine.
So now we're good shape. These are all in terms of either cosine or just a constant. This is involved sine, so we can use this u substitution at this point. So we let u equal the cosine of x, and therefore du, which is what this part is going to be negative the sine of x dx, because the derivative of the cosine is negative sine. So this is, we have to rewrite that slightly by putting a negative sign in there. So let me just erase that.
Multiply both sides by 5.
So that becomes negative the sine of x dx. And because I put a negative there, I have to put a negative outside.
The sine is the cosine.
So now we can do this u substitution. So we have 1 minus u squared times du. And we have a polynomial. We just have a constant in the first part. So the first part of the integral will be the integral of du, which is just u. And the second part is the integral of u squared, which is u cubed over 3. And we got our arbitrary constant at this point because we have completed the integral. And now we do the substitution back in. So we're getting negative the quantity cosine of x minus cosine cubed of x over 3 plus c, and we typically like to have the positive part first. So if we have a negative times a negative, that would become a positive. So the final answer would be cosine cubed of x over 3 minus the cosine of x plus c.
5 cosine of theta.
So that's the answer.
D theta. 5 cosine theta, 5 cosine theta, 5 sine theta. So those cancel out. And what I end up with is cosine squared theta d theta divided by the sine of theta. And I got another 5. I got a 5 here from there. 5 cosine squared theta. So what possibilities are there? We could rewrite it in terms of sines and cosines. We could use the Pythagorean identity to replace this. I think that makes the most sense to me. So what we'll do is the cosine of theta is equal to 1 minus the sine of theta squared. Cosine squared is equal to 1 minus sine squared. We divide by the sine.
Recording started.
This is problem 10, section 3, chapter 8. Okay, so this is the first problem that we've done that actually doesn't have just x as the argument in the trig function, but it's really not much difference. So this is a little slightly different than problem number 8 in that we've got x over 3. So we're going to do the same kind of thing. We're going to take one of the cosines, so we'll have cosine squared of x over 3 times the cosine of x over 3. That's the cosine of x cubed if we multiply those out. So we're going to make u sine because we're going to use the Pythagorean identity to convert this to sine, and then we'll have this is u and this part is du. So let's first use the Pythagorean identity, which says that we can replace sine squared, cosine squared with 1 minus sine squared. So we'll have 1 minus the sine squared of x over 3, and that whole thing times the cosine of x over 3 dx. So we'll let u equal the sine of x over 3, and therefore du is not going to be the cosine of x over 3. It's going to be 1/3 because we'll use the chain rule, which says we take the derivative of the sine, which is the cosine, and then we multiply that by the derivative of the argument in the sine. So we'll end up with cosine of x divided by 3 times the derivative of x over 3, which is 1/3 times dx. So we get du is 1/3 times the cosine of x over 3. So before we can make the substitution, we have to make sure we have the 1/3 here. So to do that, of course, we're going to multiply by 1/3 here. We're going to divide by 1/3 there. So let's do that. Let's put up a second page. So our original, we're going to take this one and we're going to multiply by 3. And then we'll multiply this by 1/3. So we can see what we have here is we have du, and here we have 1 minus u squared. So we'll have 3 times the integral. So we make our u substitution 1 minus u squared du. Okay, so we have a constant, a polynomial, so when we integrate that, we'll have u minus u cubed over 3 plus our arbitrary constant c. And then we'll make the substitution back in, so we'll have 3 times the sine of x over 3 minus the sine cubed of x over 3 divided by 3. The whole thing plus c. If we multiply the 3 out, we distribute the 3, we'll have 3 times the sine of x over 3 minus the sine cubed of x over 3 plus c. And remember, the sine cubed of x over 3 is the same as the sine of x over 3, the quantity cubed. So that's problem number 10, and it is the correct answer.
Recording started.
This is problem 13, chapter 8, section 3. So we've looked at cases where the exponent in the cosine is odd or the exponent in the sine is odd. This is the first case we looked at where the exponent is even. And so to do that, we use the power reducing formulas that we have that are in the front of the book. They're also in section, I think they're in section, yeah, they are, page 534 at the bottom of the page. You have two power reducing formulas, cosine and sine. So the formula that we're going to use is shown as the cosine squared of x is equal to 1 plus the cosine of 2x divided by 2. And in this case, x is really 3x. Okay, so we're going to, for x, we're going to put in 3x. So we can say that the cosine squared of 3x is equal to 1 plus the cosine of 2 times 3x divided by 2. And that's going to be equal to 1 plus the cosine of 6x over 2. So we can replace this, we can place that with that. So let's go ahead and do that. Let's put it up on their page. So what we're looking at now is the integral of 1 plus the cosine of 6x divided by 2 dx. And we just make that into two separate fractions. So we'll have the integral of 1/2 plus the cosine of 6x over 2 all times dx. So we then can take the derivative of those, and we don't have to do use substitution to be able to get it to fit into a simple integral rule. So the first part is we get 1/2 x. The integral of dx is x times 1/2. And the second part is the cosine of 6x. So we're going to have 1/2 times, and we've seen before that when you integrate this, you have to have 6 dx to fit it into the form of the cosine of u du. So we'll have to have 6 dx here, which means we'll have to divide by 6 outside, and then when we integrate it, we'll have the integral of the cosine of 6x will be equal to the sine of 6x plus our arbitrary constant. And again, you can always check it, because when you take the derivative of this, just the derivative of the cosine is sine is the cosine. So you'll get the cosine of 6x. Then you have to take the derivative of the argument in the sine, which is derivative of 6x is 6, so the 6 will cancel out, and you'll end up back where you started. So the final answer is just multiplying these two terms together. So we'll get 1/2 x plus the sine of 6x over 12 plus c, or you could write it as x divided by 2 instead of 1/2 x. It's the same thing. Sine of 6x divided by 12 plus c. So that's the situation. The book actually has the answer where they factor out a 12th, and so 6/12 will give you a half, so that's why you put 6 in there, and then you'd have the second term, which would be sine of 6x, whole thing with the arbitrary constant c added to it. And the only advantage of this is that here you have two fractions, there you just have one fraction, which is just a constant down front. Okay, so let me get the screen up for you. So this is going to be problem number 27, section 8.3. So this is one of these secant tangent trig integration issues problems. So we have the secant to the fourth of 5x dx. So, either we're going to take a secant and a tangent and separate them, which we don't have any tangents, so obviously we're not going to do that. So what we would hope is that we take a secant squared from this secant to the fourth, move that over there, and what you'd have left is secant squared, and we can then use one of the Pythagorean identities to rewrite that in terms of tangent. So that's what we're going to do. We're going to rewrite this as the secant squared of 5x times the secant squared of 5x dx. So that's the same thing. And then we're going to rewrite this secant squared of 5x as tangent using the Pythagorean identity, which I'm looking for it because I can't remember it, but since I can't remember it, I'm going to derive it and I don't need to put the 5x in there for the derivation. So what I do is I need to have the tangent, so I divide by the cosine squared of x, and I divide by the cosine squared of x, and I divide by the cosine squared of x. So what that leaves me with is tangent squared x plus 1 is equal to secant squared x, because 1 over cosine is secant. So that's the identity I want to use, so I can substitute that in. So I'll have, for this secant squared, I will have tangent squared of 5x plus 1. And then I multiply that by the secant squared of 5x dx. So now, because the derivative of the tangent is secant squared, we can do a u substitution. Now, as far as the secant squared part is concerned, the integral of the secant squared is just the tangent. So okay, sorry for the interruption. I got a knock on the door, so I went to answer it. Okay, so let's break this into two integrals, because one will be kind of a u substitution kind of integral, and the other one just be a straight integral. So if we take the tangent squared of 5x multiplied by the secant squared, that's 1. We're going to multiply it by dx, and then we'd have plus the integral of just the secant squared of 5x dx. Okay, so for this part of the integral, we're going to let u equal the tangent of 5x. Therefore, du is going to be equal to, okay, we have to use the chain rule here. So the derivative of the tangent is going to be the secant squared of 5x. The derivative of 5x is just 5, and then we multiply the whole thing by dx. Over here, we're just going to find the integral of secant squared of 5x, which I guess we still have to do. Let's use v instead. Just be explicit about this. V would be equal to the, actually v would be equal to 5x. And so dv would be equal to 5 dx. So now we're going to rewrite each one of these, this one in terms of u, this one in terms of v. So we need to get 5 secant squared of 5x dx. So I'm going to go ahead and rewrite it down here. What we'll do is we'll divide by 5 here. We'll put the tangent squared of 5x, secant squared of 5x, and then I'm going to have the 5 that I'm going to take from here is going to be matched up with dx. So actually it's going to be 5 secant squared of 5x dx, which is du, and then we'll have u squared. Okay, so that's the first part. And the second part, we'll do the same thing. We need 5 dx here, and we don't have 5 dx, so we'll take 1/5 the integral of the secant squared of 5x times 5 dx. So that 5 and that 5 cancel out and give you 1. So now what we can do is we can do the u substitution, u and v substitution. So the first integral becomes 1/5 the integral of u squared du. So u is the tangent of 5x, so this is u squared. This is 5 secant squared of 5x dx, which is du. The second integral would be 1/5 the integral of the secant squared of v dv. Now both of these are on page 520 as far as simple integrals. The integral of u squared. Let's go to the next page here. So let's put okay, so the integral of u squared is u cubed over 3. So we'd have 1/5 u cubed over 3. And then we'd have 1/5, the integral of the secant of v would be equal to, secant squared of v would be equal to the tangent of v plus our arbitrary constant c. So now we've done our integrations in terms of u and v, and then we substitute back in. So we'll end up with 1/5 u cubed. U is the tangent of 5x cubed over 3 plus 1/5 the tangent of v. V is 5x plus c. And the final answer would be 1/5 15th tangent cubed of 5x. We're just writing that differently. Plus 1/5 the tangent of 5x plus c. And you could factor out a 15 and you'd end up with, since this answer's in the back of the book, what they've done is they've factored out 1/15th. So you have 1/15th tangent cubed of x plus, we have 3 times the tangent of 5x plus c. Actually, you could have factored out the tangent of one more step here. So you'd have, if you factored out the tangent of 5x as well, because that's also a common term, you'd end up with, this would just be 3 plus the tangent squared of 5x plus c. Okay, so that's the answer in the back of the book. This one will be acceptable. This one's just a little bit simplified. Okay, so this is problem 31, which I apparently forgot to do originally. And my cursor's not working here, so let me turn it on and off again, see if that works. There we go. So this is problem 31 in the trig integration section. So, so you have 31, it's the tangent to the 5th of x over 4 dx. So the question is, what the heck do we do here? And let's just go to the book and see if there's any explanation. If the power of the tangent is odd, this is number 2 on page 537. If the power of the tangent is odd and positive, save a secant tangent factor and convert the remaining factors to secants. Then expand and integrate. If there are no secant factors and the power of the tangent is even and positive, convert tangent squared to secant squared factor. So that's not, doesn't work. So, so I think what we're going to do is we're going to convert tangent to 4th to secant and see what happens. I'm just thinking about what could happen here. Okay, let's just try something. So if the Pythagorean identity, the one that I always remember, is this one. So if I divide both, if I divide everything by the cosine squared, then I get that tangent squared x plus 1 is equal to the secant squared of x. 1 over the cosine is the secant. So if I solve for the tangent squared, I'll get secant squared minus 1. Okay, so now if I rewrite the original expression, tangent to the 5th, as tangent squared of x over 4 quantity squared times tangent of x over 4 dx. So I get, when I square this, I'll get tangent to the 4th, and then multiply by that, I'll get tangent to the 5th. Now what I'm going to do is I'm going to substitute in the Pythagorean identity that I just did below here. So I'll get secant squared of x over 4 minus 1 quantity squared times tangent of x over 4 times dx. And if I use FOIL on this, where I multiply this by itself, I will get secant to the 4th of x over 4 minus 2 secant squared of x over 4 plus 1 all times the tangent of x over 4 dx. So, yeah, so that's going to work out. So what we'll do is we're going to have three integrals. We're going to have the integral of the secant to the 4th of x over 4 times the tangent of x over 4. So that's from this multiplied by that times dx. Then I'll have negative, I'm going to factor out the 2, negative 2 secant squared of x over 4 times tangent of x over 4 times dx. That's this part. And then the final part is just going to be the integral of the tangent of x over 4 dx from 1 times that. Now, what we can do is, the derivative of the secant is a secant tangent. So if we take one of these secants and put it over there, so we have secant cubed of x over 4 times secant of x over 4 times the tangent of x over 4 times dx. So that's this one, and I'm just separating off the secant. So that's the first term. The second term, I would do the same thing. So we have negative 2 integral of the secant of x over 4 times the secant of x over 4 times the tangent of x over 4 dx. And then the final one, of course, is just the integral of the tangent of x over 4 dx. So now we're going to use a substitution. We're going to let u equal the secant of x over 4. So the derivative of the secant is the secant times the tangent. So we get the secant of x over 4, tangent of x over 4, all times dx. And yeah, I'm just trying to make sure if I remember. Yeah, this 1/4 thing doesn't come out or anything, because what we're doing is, if you use the chain rule, the derivative of the secant of u, if we go to page 373, let's just check this out, make sure we're doing this right. 376. So it says the derivative of the secant, well, actually we do have to worry about it, secant of u, tangent of u times u prime. So we actually do have, this is multiplied by 1/4, because this is the du part, the u prime part. So what we see is that secant x over 4 tangent of x over 4 dx is equal to 4 du. So you get 4, multiply both sides by 4, you get 4 du is equal to secant of x over 4 times tangent of x over 4 dx. And that's what I have. So all these are going to become 4 du, and this will be the secant cubed of u. But that's u cubed. So the first integral will become u cubed times 4 du. The second integral will be negative 2 times the integral of u times 4 du. And then the final one is the integral of the tangent of u. So we're going to have to, okay, so let's do that second part. We'll call that v. V is equal to the tangent of x over 4. So dv is equal to the derivative of the tangent. Well, now we don't have to worry about that. Or do we? Yeah, I guess we do. Okay. So dv is going to be equal to, no, we don't have to worry about that. Because if we go to page 383, you'll see that the integral of the tangent of u is, well, yeah, sorry. So let's do the second part. So v is actually equal to x over 4 in this case. So dv is equal to 1/4 dx. So dx is equal to 4 dv. So if we go back here and we change this, we actually have plus the integral of the tangent of v times 4 dv, because dx is 4 dv. And so now we do have it set up like we have it on page 383. Okay, now we integrate all these with respect to u and v. So the integral of u cubed is u to the 4th divided by 4, and we multiply by 4 from this constant. So let me just put that constant out front. So I'm going to take the 4, move it out front, and then multiply by that. The second part will be, let's factor out the 4 and the 2 is already factored out, so we get -8. And then the integral of u du is u squared over 2. And then the final integral, the integral of the tangent, if we go to page 383, is negative the natural log of the absolute value, the cosine of v in this case, all plus arbitrary constant c. Oh, I forgot the 4. So we've got -4. So the 4 comes out. You get a negative sign when you integrate the tangent of u. And now we can substitute back in u and v. So these cancel out. So we get secant to the 4th of x over 4 minus 4 times the secant squared of x over 4. Okay, 8 divided by 2 is 4. Plug in u, and then finally we get -4 times the natural log of the absolute value, the cosine of v, but v is x over 4. And we add our arbitrary constant c. So I think that's correct. I'm going to stop the record for right now and check the answer. Well, that was interesting. So the answer in the book is tangent to the 4th of x over 4 minus 2 tangent squared of x over 4 minus 4 times the natural log of the absolute value of the cosine of x over 4 plus c, which is sort of like mine, but not exactly. And the reason is, okay, so what they did was, the bottom line is they're the same answer once you convert them using the Pythagorean identity. So this was the original integral, and what they did was they took tangent squared, so you take tangent squared of x over 4 times tangent cubed of x over 4 dx. So rather than having tangent to the 4th times tangent, they had tangent squared times tangent cubed. Okay. So then they converted the tangent squared into 1 minus secant, or secant squared minus 1. secant squared of x over 4 minus 1 times tangent cubed of x over 4 dx. Then they multiplied it out, and so the first integral is tangent cubed of x over 4 times secant squared of x over 4 dx, and the second one will be negative tangent cubed of x over 4 dx. So in this case, say rather than du involving secant times tangent, it was the secant squared, so u is tangent instead of secant. Okay, so you go through this whole thing, and here tangent cubed, then they change that to tangent squared times tangent. I take the tangent squared and change that into secant squared minus 1, blah, blah, blah. Go through this whole thing, and they get this answer. But if you convert these using the Pythagorean identity, using secant squared minus 1 is equal to tangent squared, and you simplify, you get my answer. So 6 1/2 dozen the other. You can actually solve it both ways. Obviously, that's hard, and just try to follow it and kind of understand a little bit about what I'm doing, but it's definitely fairly complicated. Okay, this is problem number 35, section 3, another trig integration problem. So this one is fairly straightforward. So this is one of the tangent secant ones. Actually, this is just too easy. But anyway. So again, with tangent secant, you're either going to take a tangent and a secant and group them with dx, or you're going to take it secant squared. Now the wrong choice would be if you took tangent secant, and if you did that, you would end up with, instead of squared, you just end up with tangent secant, and then you'd have tangent x secant x dx. So if that were du, this would have to be, u would end up being the secant, because the secant, derivative of the secant is secant tangent, tangent secant. So you look over here and you say, okay, I've got tangent and secant, but I need just secant. The problem is that I have tangent, and I don't have tangent squared, so I can't use any of the Pythagorean identities. So that's not a good choice. Whereas if I make the other choice, if I take, and really I'm not doing anything different because the secant squared is already there, but I'm just going to put them in parentheses. So the secant squared is the derivative of the tangent. So if I'm at u equal to tangent of x, then du is the derivative of the tangent, which is the secant squared, and then multiplied by dx, because I have a differential. So I can now rewrite that original integral as u squared times du. And when you integrate u squared du, you get u cubed over 3 plus my arbitrary constant. Then you make the substitution back in. So the u cubed becomes tangent cubed of x divided by 3 plus c. So that is the answer. So that's about as easy as it gets with these things. Okay, this is problem 36, section 3, chapter 8. This actually fits the examples that we did in class much better. So this is going to be very straightforward. So we're going to have the secant squared of 2x is going to be, and times dx will be du. I'm just going to let the tangent be u. So we just do a direct substitution. And so we'll get the tangent of 2x as u. So du is equal to the derivative of the tangent is the secant squared of still 2x, and the derivative of the argument is 2, and we multiply the whole thing times dx. So that's our substitution. So what we would do is we would we can multiply by 2 here, so let me just put that at the end. Put those all together. And so we'd have to consequently divide by 2 outside. So 2 sine squared 2x dx is du. This is u. So we just have 1/2 u to the 5th times du. And so we integrate that, and we'll have 1/2 u to the 6th over 6 plus our arbitrary constant c. And then we substitute back in. So we'll end up with the tangent of 2x quantity to the 6th power divided by 12, because 2 times 6 is 12, plus c. And then we can rewrite this in its more compact form. And so that is our final answer. Okay, this is problem 40 in section 8.3. So we have the tangent cubed of 3x dx. So what can we do here? Well, the normal procedure was you put secant squared in there, and then you would match that up. But in this case, it's a little bit different. What we would still use the Pythagorean identity for secant and tangent. But I would solve for the tangent. Square root of x is equal to secant squared of x minus 1. So in this case, I'm actually having to do the substitution before I decide what u and du is. So we'll see if that helps any. Now what we're going to do is we're going to take one of the tangents. So we're going to say we have tangent of 3x and tangent squared of 3x times dx. So this is tangent cubed of 3x. And then I use the Pythagorean identity on that. So the integral of the tangent of 3x times secant squared of 3x minus 1. So normally you're used to the Pythagorean identity just being x, but if it's a constant times x, then it still applies. You just have to have 3x in each one of the terms. So now what we have is we have two integrals. We have tangent of 3x secant squared of 3x and then we have a second dx for the dx. Then we have minus the second one, so we have negative 1 times the tangent, so we'll have negative tangent 3x dx. The first one you can solve using u substitution. So the first thing we'll let u equal tangent of 3x. And the thing here, we have secant squared, which is the derivative of the tangent, so we know that's already set up in good shape. So du, again, with a trig function, you can use the chain rule, and what you'll end up with is 3, which is the coefficient, times the secant squared of 3x times dx. If it was the tangent of x, it would just be secant squared of x. If it's tangent of 3x, it's 3 secant squared of 3x. If it's tangent of 5x, it's 5 secant squared of 5x. So this doesn't change. The argument doesn't change. You just get this extra constant out front. And that would be from the chain rule. You would, you'd have this f of u would be 3, would be tangent of u, and u prime of x, or u of x would be 3x. So u prime of x would be 3x dx. That's where the 3 comes from. So that's going along with this one. So the first integral we would rewrite as, well, first we have secant squared 3x dx. So if we solve for secant squared 3x dx, it's du divided by 3. So this becomes u times du divided by 3. And the second part we'll just leave as it is. This is going to be something that's in the integral tables, 383. So I go to 383, and the integral of the tangent is negative natural log of the cosine. So the first integral will be 1/3 from the 3 here times u squared over 2. The integral of u du is u squared over 2. The second one will be, okay, so if you look at it, it says that the integral of tangent of u du is negative natural log of cosine of u. So we could use u substitution again, except u in this case, the second part, let's use a different color. The u in the second case would be 3x. du would be equal to 3 dx. So then, therefore, dx is equal to du over 3. Let's use w instead, since we're already using u. Okay, let's change that to w. dw divided by 3. Okay, so now if we go to the next page, this second part, well, before we do that, this becomes minus the integral of w, or the tangent of w, tangent of w times dx, which is dw divided by 3. So again, we get 1/3 because we have that 3 from using this u substitution. And then we have the integral of the tangent. And the integral of the tangent, according to page 383, is equal to minus the natural log the absolute value of the cosine of w. And we add our arbitrary constant c. Finally, we just substitute in u, so we get 1/6, and then u squared. U is tangent of 3x, so we get tangent squared of 3x. And then a negative times a negative is a positive. We have 1/3 times the natural log of the absolute value of the cosine of w. W is 3x. Now, the other way of doing it was, when we have these integrals that have a constant inside the argument, when we integrate it, we divide by the constant. So I know to divide that by 3. So I get 1/3, and then I have the natural log of the absolute value of the cosine of the argument. That doesn't change. The argument never changes during integration. You may end up with constants out front. And I'm just going to double check that before I declare victory. 1/6 tangent squared 3x plus 1/3 natural log the absolute value cosine of 3x plus c. So that is the correct answer.
Recording started.
Okay, we're doing problem 53, which is one of the cases where you have the argument in the trig functions are different. So there's a trig identity that can convert this into something that we can integrate. And so if we go to page 539, we see that there are 3 formulas, one involving the sine, 2 sines, one involving sine, cosine, one involving the 2 cosines. So this one is the sine. And what the formula says is that the sine, not the sim, but the sine, so the sine of mx times the sine of nx is equal to 1/2 the cosine of m minus n x, and then still multiplied by 1/2 is the cosine of m plus n x. Okay, so what is m? Well, m is equal to 1 and n is equal to 3. And we have theta instead of x. So what we can do is we can convert the sine of theta times the sine of 3 theta into, let me move that over so we possibly get this all in one line. So we have 1/2 times the cosine of m minus n, which would be -2 times theta, minus the cosine of m plus n, which is going to be 4 times theta. So let's go one more step here. So we have the cosine of negative theta minus 1/2 the cosine of 4 theta. So we went from a product of sines to a sum of cosines. So now the original integral can be rewritten. What we'll have is the integral of, let's just put 1/2 out here because that's a common term, cosine of -2 theta plus, actually minus the cosine of 4 theta, and both of those times d theta. So we can do that. The integral of cosine is the sine. We're going to have a -1/2 out front. And so we'll have a -1/2 the sine of -2 theta. And secondly, we'll have -1/4, actually positive. It'll be negative sign from here, and then we'll get 1/4 from when we use the u substitution. So that all plus the arbitrary constant c. So multiplying the half out, we get -1/4 the sine of -2 theta and -1/8 times the sine of 4 theta plus c. Now we can actually rewrite this -2 theta because of the sine. Let's just plot the sine and just do a sketch. But this relates to odd and even functions. So here's the x and y axis, and the sine looks like something like this. Okay, so this is odd because f of x, or actually f of -x is negative f of x. So what we could say is, we can say that f of -x is equal to negative f of x. So that's odd. And so if we we can change the sign of this to positive theta, and we can change that to positive. So we end up with, so it would become positive 1/4 the sine of 2 theta minus 1/8 the sine of 4 theta plus c. So again, that's problem number 53, and I'm just making sure I did it right, which I did. They actually show the result in the book. They factor out an 8, which is 2 sine of 2 theta minus the sine of 4 theta, the whole thing added to the arbitrary constant c. Okay, so that's problem number 53.
Recording started.
This is problem 65, chapter 8, 6, and 3. So we're going to do a definite integral involving trig functions. We've actually done one very similar to this just a second ago. Well, for me it was a second ago. For you it may not have been a second ago. But we have a even power of sine, so we can use the power reducing formula. We used the cosine one last time, so we're going to use the sine one this time. And so we go back to page 534, and we have the formula that the sine squared of x is equal to 1 minus cosine of 2x over 2. So this integral can be then rewritten as, let's put the 1/2 outside. So we'll have 1 minus the cosine of 2x dx. So now we can integrate that. So we'll have 1/2. The integral of 1 dx is just x. The integral of the cosine of 2x is going to be, the integral of the cosine is the sine. So we're going to have a sine of 2x, and then we're going to have to divide by 2 to reflect the argument inside the sine. And then we evaluate that between x equals negative pi and x equals positive pi. So let me make sure everything looks okay before we proceed further. So we're in good shape. There's two ways of doing this. You could take, just go from 0 to pi, because this is symmetric around the origin, around x equals 0. You could just take it from 0 to positive pi and multiply by 2. So that would be one option. So if we multiply by 2, we'd have x minus 1/2 the sine of 2x integral from x equals 0 to pi. That would be one way of doing it. And the advantage of that is that's 0 and that's 0, so you only have to evaluate at the upper limit. But let's just go ahead and do it using the original limits of integration. So we have 1/2 times. So you have x at pi, and then you subtract x at negative pi. So you get negative pi right there. And then we would have minus, and we have 1/2 times the sine of 2 times pi minus 1/2 times the sine of negative 2 pi. Make sure I have all the parentheses correct. Well, the sine of 2 pi is the same as the sine of 0, which is 0, and the sine of negative 2 pi is also 0. So these are all 0. And so all we end up with is 1/2 times 2 pi, because we have pi minus a negative pi, which is positive pi. So we get that, and so then you multiply it out. And so the answer, hopefully, is pi, which it is. The other way of doing it, if you did this, you would have pi minus 1/2 times the sine of 2 times pi, which would be 2 pi. So that would be the upper limit. The lower limit, you'd have 0 minus 1/2 times the sine of 0, which are all 0, and that's also 0. So you just end up with pi, x equals pi, or the integral is equal to pi, I guess, not x. So either way, you get pi.
Recording started.
Okay, we're on problem number 69, page 541, section 3, chapter 8. So this looks a little different than what we've seen in the past. But hopefully we see something that kind of sticks out at us, which is we have this 1 plus the sine of t. So my thought would be that we use the Pythagorean conjugate to rewrite this term. So we're going to take the integral off for right now. We're just going to do the trigonometry. So if we have we've multiplied by the Pythagorean conjugate, and I'm going to put parentheses around here so we make sure that we understand what we're doing. So we have 1 minus the sine of t, and 1 minus the sine of t. So we're multiplying by 1. So I'll end up with the cosine of t minus the sine of t times the cosine of t divided by 1 minus sine squared of t. That's because we have 1 times 1 is 1. Then we have sine, negative sine gives us 0, and then we have negative sine squared. And this is equal to the cosine squared. So we get the cosine of t minus the sine of t cosine of t divided by cosine squared of t. And then we can do a little algebra. And we have cosine, so we'll have two fractions. We'll have the cosine of t divided by the cosine squared of t. And then we'll have negative the sine of t cosine of t divided by the cosine squared of t. And you can see we can cancel one cosine out, so we have 1 over the cosine of t minus the sine of t divided by the cosine of t. And 1 over the cosine is the secant, and the sine over the cosine is the tangent. So in terms, we actually don't need to use any trigonometric integration type stuff. We just have to simplify it to now we can do the integrals. So that was one way. Actually, I just looked at the book and there's another way. So let's just finish it off this way and then we'll show that we get the same answer either way. So the integral of the secant, if we go back to page 520, which has all our nice integrals, the integral of the secant is going to be equal to the natural log of the secant plus the tangent. So if we integrate this, and I'm not putting the limits in yet, I'm consciously not doing that. I will once we get this to the end. Okay, so the integral of the secant is going to be equal to the natural log of the absolute value of the secant of t minus the tangent of t. And the integral of the tangent is equal to, so what we're going to have is we're going to have negative, and the integral of the tangent is negative the natural log of the absolute value of the cosine, and then we'd have c. So that looks pretty complicated, but we can use the properties of logarithms. In this case, this is going to end up being positive, so let's do that. So we have the secant of t minus the tangent of t plus the natural log of the absolute value of the cosine of t. It looks like I used a u up here because I was reading it out of the book. So that's the cosine of t. And we can then multiply this by each term and combine it to one logarithm. So we have the logarithm of the secant of t times the cosine of t minus the tangent of t times the cosine of t. Secant times the cosine is 1, so you get the natural log of 1. And tangent is sine over cosine multiplied by cosine. It will give you sine, so we have negative sine of t. So that's the integral. And if I haven't made a mistake here, I'm just looking at the answer in the book, and it has sine plus the sine of t, so I'm not sure why that is, if I've made a math mistake somewhere in here, or if I'm just overthinking this. So let me just look at it and make sure I haven't gotten the sign wrong somewhere. So the integral of the secant is secant plus, oh, okay, there we go. That's secant plus tangent. Okay, that's where I went wrong. So that's plus, so that's plus, and so that's plus. Okay, so that's right. Now, so that's one way of doing the integral. And then I could stick the limits of integration from 0 to pi over 2. So let's go ahead and do that. So let's go back over here. So now this would have the arbitrary constant added onto it. Now if we do the definite integral, then it just becomes the natural log of the absolute value of 1 plus the sine of t evaluated between t equals 0 and t equals pi over 2. So we would get the natural log of 1 plus the sine of pi over 2 minus the natural log of 1 plus the sine of 0. Okay, got too many vertical lines in there. Okay, so the sine of pi over 2 is going to be 1. So we have 1 plus 1. So we'll have the natural log of the absolute value of 2, which is positive, so it's just the natural log of 2. And the second part is sine of 0 is 0. The natural log of 1 is 0, so you just get 0. And so the final answer would be the natural log of 2. Okay, so that's one way. Now I'm going to insert, well, I'm just going to copy this thing here. Let me copy this over to another page. I'll show you the other way, which is a little simpler, but it gives you the same answer. So what we would do is you could use the u substitution, which would say u is equal to 1 plus the sine of t, and therefore du is equal to the cosine of t dt. So we can make the substitution, and we'll substitute back in and do it in terms of t instead of the u variable. So we're going to integrate from x equals 0 to x equals pi over 2, or t, sorry, of, so cosine of, so that's du. So we have du divided by 1 plus sine t, which is u, and the integral of du over u is a natural log of u. And we evaluate that between x equals 0 and x equals pi over 2. But u is 1 plus the sine of t. So we get the natural log of 1 plus the sine of t evaluated between 0 and pi over 2. And if we just go over to the previous page, you can see that's exactly the same thing. So we already know the answer. And the answer was whatever we came up with, which is what was the natural log of 2. So my initial idea was actually okay, but it was much longer. So it just proves that trig identities work, and sometimes there's a long way and sometimes there's a short way.